Hello everybody and welcome back to Algebra 2. Today we're going to be talking about 5.7, the Binomial Theorem. Let's begin. As always, let's start off with a little bit of vocab / review. So the very first part, can you identify the next number in each pattern? Well, if we start with a 1, we go to 2, 1, 2, 1, and you just got to go with 2. 1, 3, 5, 7, 9, 11, since they're all odd numbers. And then we got 100, 90, 80, 70, 60, and the next one will be 50. Now let's talk about the vocabulary builder. The word for today is going to be expand. You expand something by increasing it, stretching it out, or giving it more detail. Therefore, you can expand a power of a polynomial by doing the multiplication to find all the terms. Right? And you can kind of see what it looks like up in the top right corner. But place a check in the sentence that shows the correct use of the expand, and an X if it does not. The writer expanded the short story into a novel. Well, that does give it more detail. That's a check. The heat expands most metals. That's stretching it out, or increasing it if you will. And that's also true. The balloon expanded as all the air was let out. Well, if all of the air is let out, then it's going to be going back to its original state, so it's actually going to be doing the opposite of expanding, so that's going to be an X. The bird expanded its wings. Although we normally say extended, expanded does work for this situation. And the expanded form of 3x to the second minus 4 squared is in fact going to be 9x to the fourth minus 24x squared plus 16. That is correct. If you were to multiply 3x squared minus 4 times itself, so times 3x squared minus 4, you will get this trinomial. So circle a rule for squaring binomials that you could use to expand a minus b squared. Well, the good news with this is the fact that since we're already using our variables, the a and the b, we're going to be running into a situation where this is how people actually create formulas in a way. So this a minus b squared, we're just going to rewrite it as a minus b, and then we're going to multiply that a minus b times a minus b. All right? And when you do that, you're going to get the a squared minus an ab minus an ab, and last but not least, you'll get a plus b squared, which would give us a total of an a squared minus 2ab plus ab squared. Looking at this, the only one that seems to give us that solution is not going to be the first or the last, it's going to be that middle portion. Which is great because the expression 25 minus 10x plus x squared is the expansion of which power of the binomial. Well, we can kind of use the second portion to help us figure out the beginning. If you notice, the ends right here and here are always squared, so the 25 is the squared form. So if we take the square root of 25, or do its opposite, we'll know that our a value is going to equal 5. That's great. Same thing with the x squared. Take the square root, we now know our b value is going to equal x. So we can immediately rule out the first and the second one, mainly because one, the second has a 25 for the a, and we know it's 5, and the second portion, that first part that we talked about beforehand, is a 5 squared minus x squared. Nowhere on this screen do you see a 5 squared minus x squared right off the get-go, even in the beginning previous questions. So we know what it's going to look like in either a 5 minus x squared or a 5 plus x squared. Well, up here we did a minus b, and we got a minus sign in the middle. Well, if we did a minus sign right here, we're not going to get the positive. In order for us to have a positive right here, it needs to be a plus. And therefore, we can circle that 5 minus x squared. Now let's talk about Pascal's triangle. Pascal's triangle is a triangular array of numbers. The first and last number of each row is 1. Each of the other numbers of the row is the sum of the two numbers above it. So basically, as you can see in the beginning part, we start with a 1. We get a 1 and a 1. We add them up and we get our next middle portion to that row, which means that we now again are going to start with a 1, like it says in the beginning. We then have to add these two numbers together, so we have 1 plus that 2, giving you 3. We have a 2 plus 1, giving you 3, and then we have a 1. And then we can just start going down by just strictly adding. So we get 1, 4, 6, 4, 1. We have a 1, 5, 10, 10, 5, 1. A 1, 6, 15, 20, 15, 6, 1. 1, 7, 21, 35, 35, 21, 7, 1. And then at the 1, 8, 28, 56, 70, 56, 28, 8, and 1. So what's the purpose of learning Pascal's triangle? Well, in this case, we can actually use Pascal's triangle to complete any binomial that's being raised to a certain power by just literally plugging in these random numbers and then just multiplying out everything. So instead of having to actually go through all the multiplications of everything over and over and over again and then combining the like terms, we have now set it down to the point where all we really need to do is maybe raise a number to a certain exponent and then multiply it by this strict coefficient. And that strict coefficient we're getting is going to be coming from Pascal's triangle. So, circle the row of Pascal's triangle that you would use to expand a plus b raised to the 8th power. Well, the exponent that we're going to be talking about is that 8. The exponent that we need to find needs to be attached in the second position in Pascal's triangle, not kind of excluding that top portion. So we have the 1 and the 1 is in the second place, the 2 is in the second, 3, 4, 5, 6, 7, and then we have our 8. This number should match the exponent, and that is going to be the row in which we use. So we have a 1, an 8, a 28, a 56, 70, 56, 28, 8, and a 1. Which seems like a lot, but realize if we actually did multiply everything out, it would take forever if we're raising it to the 8th power. So we can now use this row to complete the expansion by simply plugging in all of these as coefficients. So we start with our 1, we then have our 8, 28, 56, 70, 56, we then have our 28, our 8, and our 1. Now, since the numbers that we're talking about are A and B, and they're not actually legitimate numbers yet, we can't simplify it any farther. This is completely done. Great job. So let's go a little bit more in detail about this, and let's explain the binomial theorem. For every positive integer n, where n is the exponent of the binomial that we're talking about, the piece of 0, piece of 1, piece of 2, and all that wonderful stuff, basically the coefficients of each and every one of these terms are going to be the numbers of the nth row of the Pascal's triangle. Now that's 100% true because that n is going to be attached to that exponent. However, they are going to be kind of not including that very first portion, that 1 at the very top. Our first row is actually going to start with a 1, 1, not that 1 by itself. So our second row ends up being 1, 2, 1, and you can notice that it's actually going to be, again, it's going to be the portion that has the number of the exponent in the second position. So a 1, 3, 3, 1 would be the next one. So this would be for our, if our n is going to be equal to 3, because it's going to be in the third row. So, knowing this, can we complete the row for Pascal's triangle that you would use to expand the a plus b raised to the 5th power? Well, if I were to go through that entire set and just keep on going down, so we have the 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, we have a 1, 4, 6, 4, 1, and then finally we'll have the 1, 5, 10, 10, 5, and then a 1. Which means that we're going to be given 1, 5, 10, 10, 5, and a 1. And using that line right there, can we get our 6th line after that, which is just basically adding up everything. So it should be a 1, 6, 15, 20, 15, 6, and a 1. So once again, these numbers, the 1, 6, the 15, the 20, the 15, the 6, and the 1 will be the coefficients to each and every term of the a plus b raised to the 6th power once it's been expanded. Problem 2. Expanding a binomial. What is the expression of 2x minus 3 raised to the 4th power? Use the binomial theorem. Identify the values of a, b, and the n, of course. So a is going to equal our beginning portion to the binomial, that first term, which is a 2x. And yes, we do have to include the x. Our b is going to be the second portion, or the second term, making it a negative 3. And once again, need to keep the sign. And our n is always going to be our exponent. In this case, the exponent is going to be 4. So if we had to rewrite this expression in the form of a plus b raised to the n, you would end up getting a 2x plus a negative 3 raised to the 4th power. Since we're talking about the 4th power, we know that we have to use the 4th line, or 4th row, that 1, 4, 6, 4, 1. So these are all of our coefficients. I'm going to write them in. So we have a 1. This is going to end up being a to the 4th. So our a is 2x, so it becomes 2x to the 4th, because you always start with the a raised to the 4th power. We then write our next coefficient, which is 4. We have our a to the 3rd power, and since we took away one of the powers from our a, we're actually going to add one of the powers to our b. So now it becomes b to the 1st power. So notice all of these exponents will always add to 4. So we have a 3 and a 1 now, but our b was originally negative 3, so we have a negative 3 to the 1st power. We have our coefficient of 6. We have our a squared, b squared. So our b, again, being negative 3 squared. We then add in our 4 times a to the 1st power, b to the 3rd power, or negative 3 to the 3rd power. And then we are going to add in our last coefficient, which is 1, times our negative 3, or our b raised to the 4th power. So if I had to write this in AB form, it's going to kind of look like a 1 times your a to the 4th. We then are going to be adding that to our 4 times our a to the 3rd b, which you can kind of see again, getting rid of one exponent, adding it to the b. Getting rid of an exponent one more time and adding it to the b one more time, I'm going to get a plus 6 a to the 2nd power, b to the 2nd. The a went down 1 to the 2nd power, the b went up 1 to the 2nd power. And then we would have our plus our 4 a to the by itself, or a to the 1st power, with our b to the 3rd. And then last but not least, you would have the plus 1 b to the 4th, because all of our a's will be gone, and we'll have only b's left. If I were to go through all of this and simplify it out, you have to make sure that you simplify everything straight up. So we have 2 to the 4th power times 1, which is what we're going to end up getting, which is going to end up being that 16, because 2 times 2 times 2 times 2 gives you 16. We have 2 to the 3rd power, which is going to give you 8. 8 times 4 is 32, times a negative 3 will give us a negative 96, x to the 3rd. 2 squared is 4, times 6 is 24, times a 9, because negative 3 squared is that. So we'll get 24 times a 9, which will give us 216. We have a 2 times 4 times a negative 27, give you a negative 216. And the very last one is going to be a negative 3 to the 4th power, which ends up being 81. So our end answer is going to end up being 16x to the 4th minus 96x to the 3rd plus 216x squared minus 216x plus our 81. And finally, we made it to the lesson check. Tell whether each expression can be expanded using the binomial theorem. The 2a minus 6 raised to the 4th, the 5x squared plus 1 raised to the 5th, or the x squared minus 3x minus 4 raised to the 3rd power. Well, essentially, the only thing that we need to pay attention to is which one of these are binomials. And the 2x minus 6 is a binomial, and the 5x squared plus 1 is also a binomial. However, x squared minus 3x minus 4 is going to be a trinomial. Place a check if you can use the binomial theorem to expand the expression, and an x if you cannot. And therefore, we can put a check next to, again, the first two, and we have to cross out the third one. which takes us into this last little bit. Using Pascal's triangle, determine the number of terms in the expansion of x plus a raised to the 12th. How many terms are there if you had to use the expression for x plus a raised to the nth power? Well, circle the row that we know we have to use for x plus a raised to the third. And the one that we're going to be using is actually that it's almost like the fourth row, but they call it the third row, which is 1, 3, 3, 1. And then write the expansion. Well, x plus a raised to the third will turn into a 1x to the third. We then will have a 3x squared a to the first power. We have a 3x a squared, and then we'll have a 1a cubed. In this case, the number of terms in the row of Pascal's triangle is in fact going to be equal to the number of terms in the expansion of the x plus a raised to the third, which means that it's basically going to equal 3 plus 1. Essentially, the exponent is always going to be added to 1, and that'll figure out how many terms there are going to be if we were to fully expand out any binomial number using the binomial theorem. So, circle the number of terms in the row of Pascal's triangle you would use to expand x plus a raised to the 12th power. Well, 12 plus 1 gives you 13. So we know it's going to be 13. Circle the number of terms in the expansion of x plus a raised to the 12th power. Once again, if we were to actually expand it out, it's going to be 13. And the final little bit, circle the number of terms in the expansion of x plus a raised to the n power. It's basically going to be whatever the exponent is, that n value, but plus 1. And that's it, everybody. I hope you have a wonderful day. Stay out of trouble. Don't do anything stupid. And I'll be seeing you guys in the next one.